It's late. You are trying to sleep, but you get the dreaded, "You cannot sleep now, monsters are nearby" message. Your sword just broke, and you need to craft a new one. You walk into your chest room. You're looking for where you put your diamonds after your most recent mining trip. You know you put them in one of your chests when you got back from mining. The problem is, you have hundreds, maybe even thousands of chests to look through. How long is this going to take? Maybe you'll find them instantly. But then again, maybe it'll take hours. The weird thing is, computer scientists can actually predict how long the search will take before you even open your first chest. That same idea is why TikTok loads instantly, while bad apps freeze and crash. Looking through a small group of chests is easy. You just go one by one until you find what you're looking for. But thousands? That's miserable. It is easy to see that the key variable is the number of chests you have to search through. That's when programmers start asking a different question. How does the amount of work grow as the problem gets bigger? This is what computer scientists call running time. Imagine your diamonds are in the very last chest. If you have 10 chests to search through, that's annoying, but if you have 10,000 chests, that's a disaster. In our Minecraft example, opening one chest is one step, and the number of steps depends on the number of chests we have to look through. We don't actually care about the exact seconds it takes. We care about the pattern of growth. Say we have two programs. Program A always takes 1 second to run, every single time. Program B, on the other hand, takes 1 second to run with 10 items, but it takes 1,000 seconds to run with 10,000 items. Program B becomes unusable at scale. By the end of this video, you will know exactly why. It turns out there are 3 common patterns that programmers see over and over again. The first one is surprisingly powerful. Constant time. Imagine you always label your chest with what's inside. When you need to find something, you go immediately to the chest labeled as such. Doesn't matter if there are 5 chests or 5,000. The thing you are looking for is always in the right chest. No searching required. That is constant time. Unfortunately, most searches don't always work that way. Imagine you did not label your chests. To find your item, you need to check each chest one by one until you found it. The more chests you have to search, the more time it will take. That is linear time. And then there's the really dangerous one. Imagine for a second you're at a Minecraft marketplace. Every player needs to trade with every other player. 2 players trading back and forth, just 1 trade. 4 players have to make 6 trades to trade with everybody. And 10 players needs to do 45 trades. The number of interactions explodes, even though the number of players only grew a little bit. That is quadratic time. Now remember when I said programmers can predict how long your search for diamonds will take before you even open the first chest? This is how they do it. These 3 patterns, constant, linear, and quadratic, are the basis of a system called Big O notation. It is a language programmers invented to describe these patterns quickly. The O stands for in the order of. Let's look at these 3 patterns one more time. Constant, the labeled chest, is O of 1. Linear, checking every chest one by one, is O of n. Quadratic, which is every player trading with every other player, is O of n squared. Big O isn't about being exact or precise. It's about roughly knowing how bad things get as a problem scales. Take a look at this graph of all 3 running times. Can you see the difference? You might be asking, why would anybody care about this seemingly arbitrary system? On a small scale, it doesn't really matter. But once you start growing the inputs large enough, the difference between O of n and O of n squared could be the difference between a snappy responsive app and one that freezes constantly. Imagine the developers at TikTok or Google did not care about running time. Using the internet would be nearly impossible. You sit down on the couch after a long day of work, you try to scroll TikTok, but every other video loads for a second then just immediately stops. Or maybe you go to turn on the big game on your brand new smart TV, but it keeps buffering and you miss the game-winning touchdown. Knowing Big O helps you write code that can withstand the real world without falling apart, and it is crucial for anybody who calls himself a programmer. To recap, O of 1 is constant time. It's always fast. O of n is linear time. It grows evenly with the input. And lastly, O of n squared is quadratic. It grows extremely fast. Suppose you double the size of your Minecraft storage room. It's labeled, it's O of 1, no big deal. It's O of n, it's twice as much work. It's O of n squared, it's 4 times as much work. And that's why programmers obsess over Big O. The difference between a great algorithm and a bad one isn't just a minor speed boost. It's the difference between an app that scales to millions of users and one that collapses under its very own weight. Next time we're going to look at something even stranger. Algorithms that get faster and faster relative to the size of the problem they're solving. It's one of the most beautiful ideas in computer science. So if you don't want to miss that, subscribe, and I'll see you in the next one.